Hi, and welcome to this session on architecture. Whenever people talk about architecture, you're probably going to see an image looking a lot like this. It's known as the N-tier architecture. It's the thing that's getting taught in schools. It's the thing that we've been doing for the last 30, 40 years. It's basically separating the different concerns, saying you have a front end, you have a back end, and you have some data. If we take a closer look at the data and the back end side of this, or middleware, or something to that effect, you'll see that in the middleware, on the back end here, you have your application services, you have your business logic, you have your representation of the domain, and you have some tools and things like this. And that's actually running and talking to a database. The way it talks to a database is using things like an object relational mapper or whatever data access layer you want to have on top of your data. And often at times, the domain model modeled inside your backend is very similar to what you find in the data, in the database. It's often relationally modeled even in the domain model. So traditionally, if you want to look at how a system like this runs and scales, when you get to a point with a system that where you need it to be, scale it out, or actually for reliability, you want it to actually have more instances, because if one thing goes down and on one, you don't want it to affect all your customers, and you want to be up as much as you can. You might have a service level agreement saying you have to have uptime of 99.999, and you actually have to deliver on that. So when you scale it out, either for load or for reliability, you basically add multiple instances of your system running at the same time, and you stick a load balancer in front of it, and you do something like a round robin strategy or other strategies where you're distributing the load across these different nodes. And whenever you reach a point where you need more and you need to be able to take on more users of your system, you just follow that pattern and scale out. At one point, you're going to reach a kind of a barrier where the database is now your bottleneck, because all these nodes are pointing to the same database and all your users are pointing to that same instance. And that means now your database is the bottleneck. And you can solve that by, making the database, that server, bigger, if it's possible to make it bigger. And maybe there's a cost related to making it bigger. Maybe there's a cost related to actually licensing, because some database vendors are licensing by CPUs and CPU cores. But that's how you can do it. You can scale that up. And at one point, you might actually need more scale, so you make that machine even bigger. And again, cost related to both making that bigger and licensing could be an issue. So the next level of that is typically to, scale it down again and start having replicas of the database. And the replicas are being used to read only. So you write to one place and you replicate that across to different read stores, read representations of that same database. And that makes it easier to scale, because now you're kind of scaling out in the same fashion or a similar fashion that you were doing on the compute side. You now have multiple instances that each of these can go kind of a round robin style across to be able to scale that out. But at one point, you get to the point where this is either too costly or it's actually you can't really scale in this manner anyway. And multiple reasons will lead you down to the path of we have to think differently about it. And what you tend to do is add caching to the mix. So caching meaning you keep some of the data in memory. You can keep it in memory either on the different nodes, the compute nodes, or you can have a distributed cache that keeps some data actually ready for you to go get. So you don't have to do a full round trip back to the database to get that data. What you're introducing into that is the concept of eventual consistency, because now you have you're not really consistent with the database. Whenever you're writing to it, doesn't mean that you're actually updating the cache. So you have to come up with a good strategy for dealing with that. You have to figure out how will my users not look at stale data and have a good user experience with this. Some data is okay to actually, it doesn't need to be up to date, but while others are, so you need a good strategy around caching. But what if we thought differently about the whole thing? So let's take a domain, e-commerce, and let's look at product as a entity in that domain. So if we were to model this, so take what we just saw, and in modern systems you would have like a REST API where you're talking about product. In something like ASP.NET Web API, that would be a controller, a product controller that enabled you to go and get stuff, get products, or get a particular product, and then also be able to do updates against it through doing post. And you could also do put, or you could do delete, or whatever HTTP verb. What that would do then is just talk to the application services and use your domain model and eventually talk to the database. So from that model, what we've already seen in a controller like that, and actually REST APIs, they're introducing the concept of CQS, command query separation, which is a principle coming from Bertrand Meyer back in 1987, saying that a method can only do one, either write or get. So a HTTP GET should only actually get stuff. It shouldn't affect anything. It shouldn't do state change on a database or something like this when it's getting. It should only do that thing, get. When you're doing a post, it should only actually change things. It shouldn't then return what it changed, or it should return some other state in the system. It should actually do just one thing. That principle is already kind of baked into the notion of a request response, and is a very good principle to follow. So what if you went one further and said, well, writing and reading, they're actually very different concerns. They're so different, you can actually look at it as different for scale, different for security. You would secure them in a very different way. You have probably more users looking at it than you have updating it. And if you look at e-commerce, that's very, very true, because there's a lot of users looking at your product, but there's only a few people working at the e-commerce that actually updates the product. So what if you kept them in different stores? Totally. And really just thought of them as very different things, and even went one further and said they're completely different objects altogether. They're modeled differently, they look differently, because you have different things that you want to update, and you might want to have different representations of that product for different use cases when you're reading it. And you can still have your controller sitting on top of this, just governing that. What Doolittle is bringing into the mix is actually a formalization of these pipelines, and saying you have a command, that's the only thing that can actually change things from a user, and then you have a query, that's the only way you can get things. And this is following the CQRS principle, the command query responsibility segregation principle, coined by Greg Young about 10 years ago, and is really at the core of what Doolittle is all about. It's about formalizing these two different pipelines because they are very different. A command needs to be validated. It needs to be, well, first you have your input validation, then you have your business rules that you want to apply to them before you even get into actually doing your change, right? So that's not something that you need to do on the read side. But on the read side, you want to secure it. for different, well, more users will see the product, while on the command side, there's even less users that's going to actually update the product. So at the core of Doolittle, you'll find also the concept of events. So when you send a command in, you are asking to do something. You have an intent as a user to do a change to the system. While an event is actually modeled as the truth. That's the thing that changed. So when we're talking about a command, that command goes in and talks to something called an event source. The event source is the thing that applies an event, and the event is then stored. It's stored in a very different type of database, so it's not a classical database. So your write models are actually events. And that now becomes the source of truth. These events can never be deleted. They are there forever. That means if you want to do something, so let's say you did a mistake and you want to fix that mistake, you have to do a compensating event because it will be there forever. These events are not used on the read side to get state out to the user. We have still, you can use your traditional databases. You can use a relational database if you want to. You can use a document database or any other types of storage mechanism that you can use for your particular feature. And the way we communicate state changes is through these events. So we publish those events for the read side to process. So whenever an event occurs, it will be published so that you can do whatever is right for your feature and actually have a perfect cache at this point. Because now we know when things change and we can actually update the read models, as we refer to them as, whenever they actually change. And on the event store side, where we actually store all those events, this now becomes a perfect audit trail for what has happened in your system. Alongside the event, Doolittle also stores a lot of metadata about who did it, what was the context in which it happened, time, of course, and all these kind of things going into it as metadata. So you can actually backtrack and figure out what was going on and who did what at what time. These can also be replayed at a later stage. So let's say you introduce another read model, but you want to feed off of existing events. You actually just drop in an event processor or multiple event processors for those events that you're interested in, and the system will automatically replay the events related to doing that. That means you can be future-proof for, well, new storage mechanism, new features, and all these kind of things. And the beauty about this is that you can also throw away the database. If you figure out this database is not working out as it should, you can then just throw the database and replay all those events into a more optimal storage mechanism for your purpose. So another key concept of Doolittle is actually breaking everything up. So we've now broken up the read and the write side of the system. But we go even further. We say that making a system actually consists of many smaller systems. And this is kind of the promise of what microservices has been talking about for a few years now, is how do we actually take these monolithic systems and breaking up into smaller, more digestible pieces, with the purpose of being able to actually maintain something in isolation, autonomous pieces of your system that can actually be deployed autonomously without having to be dependent on other parts of the system. Sometimes there are dependencies between them, so you need to actually be aware that something happened in another part of your system, but without having to actually explicitly integrate on a database level or something like that, we have something called event horizon. Since everything is represented as events when it comes to state changes in a Doolittle system, we can use that as the contract going between the different systems as well. So these events has the concept of generations, which is basically versions of the different events. So let's say one part of your system actually updates and has a event. That event is registered as a particular shape. It looks like this, and it has a generation or a version number attached to it. And we use that information on the other part of the system to figure out which version we're actually depending on. Because when you look at breaking up a system like this, one of the hardest problems you will get is versioning between the different systems when you're bringing it back together in a composition. Event Horizon deals with that. Event Horizon deals with the complexity of actually migrating between different versions. If you have a breaking change from one version of an event, one generation of an event to another, you will simply write a migrator that will deal with the change. And this is only important to do it when you're actually in production and have had users using your system. There's no point in writing migrators while developing for your first release of a software, obviously. So these different autonomous systems running these microservices, we give it a name based on domain-driven design. It's a bounded context. These different autonomous systems are deployable on their own, and everything that belongs to that part should be modeled together and actually deployed together. These bounded contexts are the ones that we talk about all the time, and it's a very important construct of Doolittle. With this, so part of the whole thing, a very core principle of everything Doolittle is to break down larger problems into smaller problems. Smaller problems are easier to maintain and easier to understand. So we've seen that we've broken down commands and into commands and queries. So we take in something that was one thing and broke it into two. We're seeing that we're breaking up systems, so monoliths, into these microservices, or referred to as bounded contexts. So the next level is, how do you deal with tenants? So building modern day applications today, software as a service based applications, you're going to have multiple customers coming into it. And these are referred to as tenants. And that's what we call a multi-tenanted system. Part of building a multi-tenanted system is that you have to be very conscious about data segregation. That can be a legal thing, but also a complexity in your system. If you want to, it can easily become a problem for you if one tenant is seeing the data from another tenant, or even worse, updating the data for another tenant. And you really do want to think hard about these things and partition them and keep that separate. The way Doolittle deals with this is actually have physical separation. So that means for each tenant, there is a database. So if you have your read model sitting in a database, there will be one database per tenant. That means also for event store, there will be one per tenant. And we're already breaking it up. So one of the key aspects of microservice architecture for these bounded contexts is that it's end-to-end autonomous. That means the bounded context itself also has the rule of saying, I'm not sharing the database between two different bounded contexts. I'm not sharing the event store between two different bounded contexts. So that means you have one database per tenant per bounded context in your system. You have one event store per tenant per bounded context in your system. And this is where the Doolittle resource system comes to play, to actually make sure that based on the tenant coming in your multi-tenanted application, we will give you the right database. We'll make sure you can reliably trust this and write to it, read from it, without having to think about it. You'll just be given the right connection string or the right resource representation to actually work with that. And Doolittle will keep those segregated and make sure you don't run the risk of anyone seeing another tenant's data. This is also very good for scale, because now we're breaking it down into smaller problems. It's easier to scale, it's easier to maintain, and there's a lot of benefits with this. The resource system is also capable of doing provisioning. So that means whenever you connect and you say, I have this data, and a new tenant comes, the resource system will provision a new database. It will also provision a new event store and other resources that are supported by Doolittle. So with that, I would like to thank you for your attention and hope this was useful.